feel you want to take on the challenge and do it all by yourself, you are more than welcome to do so. The project, in my opinion, is entirely doable by a single person. So I have asked two of my PT students, they independently work on that one. Took them about 3 to 4 hours to complete that one. Okay? Of course, these are PT students, they are well trained in this space, and they're super strong as well, so I do not expect you can finish this in just 3 or 4 hours. But I have allocated, in light of the time taken for them to do it, right? So I have allocated a little bit more than 2 weeks for you to work on this. There will be absolutely, take this seriously, there will be absolutely no extension allowed. Once submission deadline is passed, if you don't submit, you get 0 points. Okay? There's no extension whatsoever, unless you have a significant, kind of thing going on in your life. In that case, you need to let me know ahead of time. It's always a case-by-case situation. Then I will look at it. What are the reasons you are falling behind? Then maybe I will grant an extension, but that's extremely rare. Okay, I encourage you to get started early. So I will. That being said, I will spend some time on Lab 1 today after I finish the lecture today. Okay. So we talk about buffer, which actually is part of what you will be implementing in Lab 1. We talk about buffer replacement policy. I highlighted the problem with different kinds of replacement algorithms. The fundamental challenge is this is an online problem. You are designing an online algorithm, meaning you do not know the input in the future. And an adversary can actually look at what you do and design a really bad sequence for you on the fly. So no single algorithm actually works the best. So how do we quantify how good a replacement policy is? Obviously, there is still a difference. That being said, it doesn't mean you cannot design a good algorithm in this sense, right? It's just we have to figure out what we mean by a good algorithm in this particular context. Give you an extreme argument. LRU is basically used replacement algorithm, which I demonstrated in last lecture. It will suffer from this sequential flooding problem, right? But intuitively, LRU should still work much better than simply make a random choice. I can design another algorithm. This algorithm is very simple. I randomly select one frame with pin count to 0 to be replaced. That's my algorithm. That's it. Whenever you have a replacement requirement, I randomly select one and pick out. And that's the algorithm, right? Obviously, this algorithm, in most cases, by most cases I mean in most input, for most input sequences, you will expect LRU to perform better than this random choice algorithm, right? Do you follow me? But we need some kind of formal argument to show that LRU is indeed better than this. And this is not so trivial to show, right? Because think about all the algorithms you have learned so far. Take sorting as an example. When we say merge sort is better than bubble sort, how do you show that? Well, you show the complexity, right? Bubble sort is n squared, merge sort is n log n. Clearly, merge sort is better than bubble sort. But how do we quantify that LRU is better than random choice? How do you argue this? In terms of running time, they all are just O1. Random choice generate a random frame number and replace. LRU, suppose you maintain a heap. Heap is sorted, by the way, of from the least recent used to most recent used frame. The replacement decision of replacement can be obtained in O1 time as well, constant time as well. So running time-wise, they are identical. Do you follow me? In terms of replacement cost, meaning how many buffer misses you're going to generate, this is where this problem becomes really tricky to analyze. You don't even know the input. If you analyze the performance of these two algorithms with respect to a given input sequence, this doesn't make any sense because you can always find a sequence where LRU perform the best, random choice perform really poorly, but you can also find another sequence where random choice performs better than LRU. You follow me? And how many possible sequences are out there? Well, infinite number of possible sequences. How can you possibly analyze this? Well, but people still do. Okay, that's what I'm going to show you next. You follow me? Do all of you follow my argument so far? So how do we analyze the performance of online algorithm? We introduce the notion of competitive ratio. The idea is as follows. Okay, it's hard to compare these two guys side by side, LRU versus random choice, or LRU versus any other online algorithm for this problem. However, this is very intuitive, right? When it's so hard to compare two of them side by side, what do? Well, you compare both of them to another entity that you know the performance. And you look at the ratio of them to that third party. You follow me? Right? That's kind of the idea. That the third party that both of them will be compared against to is the offline optimal algorithm. It's the offline optimal algorithm. But still, one challenge remains. Even for an offline optimal algorithm, I explain what is an offline optimal algorithm. An offline optimal algorithm for this problem is that imagine you know the future. Meaning the sequence is given to this algorithm. The entire sequence is given to this algorithm ahead of time. And with the parameter k, which is the size of your buffer. Then design a replacement algorithm that's optimal. You cannot beat this. You follow me? So that's what we mean by offline optimal. Where the offline algorithm can only see one request at a time. You don't see the entire sequence. You only see one request at a time. And the next request is only given to you after you have made a decision on what to replace. Okay? That's the major difference between offline and online. Okay? But still, the offline optimal algorithm, the performance can vary dramatically. Depending on your input sequence. You follow me? For example, suppose that's my input sequence. Or in fact, yeah, that's my input sequence. So I have all the ones appear together, all the twos appear together, all the threes appear together. If you are offline optimal, the trick is you see the whole sequence ahead of time. You follow me? So what should you replace? Well, you should always replace the page with the smallest page ID. Because that will never appear again. That's the optimal algorithm here. You follow me? Yes? So the offline optimal, this seemingly, very random algorithm replace the page with the smallest page ID actually works the best. Right? Because the future sequence always requests for page IDs larger than the ones that have appeared. But this is the seemingly random choice, right? So how do we quantify this particular phenomenon, which is for different input sequence, even the optimal algorithm may have very dramatically different cost? Well, the idea is we compare the ratio between your online algorithm and the offline algorithm on a particular input sequence. Okay? So this capital I represent the set of all possible input sequences. Obviously, the set of this is an infinite set, right? Suppose okay, let me given one assumption, which is let's say I have m distinct page IDs, small m distinct IDs, and capital N number of requests in total. You follow me? Capital N number of requests in total. Can someone tell me what's the size of this? given these two parameters. Okay. Total, I have n requests, and I have n distinct page IDs that I can request on. What is the space of this? What's the input space? Huh? Who said something? Raise your hand. Say again.
M raised to n.
Slowly. What's the size of it?
M.
M
Raised to n.
raised to n. M to the power of n. Can you explain why?
There are n pods, and we can have like m. Every box can be filled with m.
So every request, how many choices you have? M choice you have, right? And each choice is independent from all the preceding choices you have made. You're free to select whatever you want out of this n pages. And you have a total of n trials you can run. So obviously the possible number of sequences is m to the power of n. Right? This is basic. Okay, you guys need to understand this this is like really trivial stuff, right? So m to the power of n. So this is a huge number if you think about it, right? M is big, n is even bigger. However, what we are saying is for each possible sequence, there is a cost of running your online algorithm over that input, and there is a cost of using the offline optimal on that input I. Keep in mind, this offline optimal is a super powerful offline optimal algorithm, meaning that you can even think about this as kind of like a hash table-ish algorithm. For different input sequence, I can behave totally different. For the sequence I just given now, if I say that, my algorithm, my offline optimal is to replace the page, always replace the frame with the smallest page ID. But then for another input, my offline optimal, same algorithm, can behave totally different. So you can imagine this offline optimal as a super big case statement. Case 1 do this, case 2 do this, case 3 do this. In other words, it always performs the best on any given input. You follow me? So that's this super powerful offline optimal we're talking about. You follow me? Yes? So you can do different things with respect to different inputs in order to achieve the smallest cost for any given input sequence. Okay? So in the worst case, you can imagine that algorithm is a case statement with these many possible cases. And for each case, I specify what to do. You follow me? Of course, you may argue, wait a minute, then that offline algorithm, the space you need to describe the algorithm is at least m to the power n already, right? Because you need that many case statements. How can you write a function like that? Well, don't worry about that. Let's imagine we have a way to do that. And that's the powerful part of this definition. What this definition says is, okay, for that same input, you run your online algorithm, right? LRU, MRU, whatever it is. But the only requirement is you have to make a decision before you see the next request. And there is a cost of running your online algorithm on this given input. In fact, there is a cost for running this algorithm over different inputs. 1, 2, until input m to the power of n. You follow me? Then I look at the ratio between U cost and the smallest possible cost one can hope for over that input. You follow me? And then I look at the max ratio between U performance and the offline optimal over the entire possible input sequences. What this value tells you, if you think about it, what does this tell you? This tells you, in the worst case, the gap, the performance gap between the U online algorithm against the offline optimal over all possible input sequences. Obviously, this ratio, you can now use this ratio to compare the performance of one algorithm against another online algorithm. obviously, if you use this notion, then LRU, the worst ratio obviously should be better than the worst ratio of random choice, obviously. Because random choice, the ratio can be as big as what? As big as n. So for the random choice algorithm, this ratio obviously is n. In the worst case, right? Because the worst case, you always replace the one you want to request next. Your random choice happens to be the worst possible choice you can make. Right? So for that random choice online algorithm I just designed, this ratio is n. What's the ratio for LRU and MRU and others? Okay, and this is the result for LRU. Okay, for LRU, it obviously depends on the size of your cache. The size of your cache, right? Why the size of cache matters? Why the size of cache matters? Well, imagine in the worst case, right? In the extreme case where your cache size is 1, meaning there's only one frame. Think about this in the extreme case, right? Do you follow me? There is only one frame in your buffer. Then any online algorithm may miss on every request. Right? I can always imagine, because you can always design an input. You observe what the online algorithm does, and you basically request the one that it has just replaced. And because you only have one frame, right? Any online algorithm cannot hope for doing better than this. So when k equals 1, any online algorithm will have n misses. By the way, but this cost might not be n. The number of cache misses by any online algorithm is n. The ratio is not necessarily n, because you need to compare that against the offline optimal. The offline optimal, though, what is that? The offline optimal, but you're looking at the extreme case, right? The extreme case. What is the this ratio in the extreme case? When there is only one buffer frame, what kind of offline optimal do? What kind of offline optimal do? Well, it depends on this value here, this and value here, right? This and value here, this and value here. If you have, for example, n equal to 1, what happens? Can someone tell me in this case? N equal to 1 and k equal to 1. What happens? And n can be a really big number. N can be a billion, whatever. What's the value of this ratio? The cost of any online algorithm compared to the offline optimal. It's 1, right? Because no matter what algorithm you use, you will not incur any cache miss, except the first request. But that first request, the online and offline algorithm both have to pay that cost. You follow me? So this simple kind of example illustrates to you that this is a very sophisticated problem, right? It depends on the specific value of all these different parameters. So this is the competitive ratio for LRU. So you can read this yourself, but the basic idea is, okay, I will skip this. I think you can read it yourself. Now another thing I want to introduce is sometimes comparing the performance of an online algorithm against an offline optimal is just hopeless, because offline optimal can do so well that no online algorithm can even reach a reasonable ratio within the performance of the offline optimal. That might be the case for a lot of problems. In that case, it doesn't make sense to compare two offline algorithms against two online algorithms against an online algorithm. Two online algorithms against one offline optimal algorithm, because both of them compared to any online algorithm compared to the offline optimal is so bad, it makes no sense to compare them against this offline optimal anymore. Do you follow me? Okay? Okay. In that case, how do we compare the performance of different online algorithms? Well, we use this what we call instance optimal. The idea is as follows. Okay, forget about offline optimal. It's too good. Nobody can compete against it. But that's fine, because it's an unfair comparison from the beginning, because you know everything and I only see one request at a time. So this comparison in some sense is not fair to begin with. And your goal is to design a good online algorithm. Your goal is to design a good online algorithm with that limited budget. So let's look at what the best you can do in that particular setup. So that's the idea behind instance optimal. The idea is for any given input I look at the cost of running your online algorithm over that input I. So that's this value right here. And I compare against the best online algorithm on that input sequence I. Note that this A star is not quote-unquote the optimal online algorithm for all possible input sequences. It is only optimal with respect to this one input, one particular input. It may perform really bad on some other input sequences, but it performs the best on this given input. That's why this algorithm is denoted as with a subscript input I. So it is optimal with respect to only this one particular input sequence. You follow me? Then I look at this ratio for a given input I on a given online algorithm. Then the instance optimality of an online algorithm is simply defined as the max possible value of this ratio. Okay? So in the worst case, what's the gap between an online algorithm of your interest, to the optimal online algorithm on any given input? And this is again very strong notion, right? Because you are not comparing one online algorithm against another online algorithm. Rather, you are comparing one online algorithm fixed against the best performer on each possible input sequences. Where when you change the input sequence, you may be comparing against a different competitor which performed really well on that sequence. So imagine kind of like a soccer match, right? Suppose Brazil really played well under hot weather only. Right? Of course, that's a fake argument. They play well almost anywhere, right? But suppose that's the case. They play really well only under hot weather. And then there's another team like USA. You can pretty versatile. You can play under all weathers, but not necessarily in any weather you are not the best. But you can play in all weathers. And then another team, Germany, play really well only in cold weather, but otherwise perform really badly. Brazil perform really good in hot weather, but perform badly otherwise. So how do you quantify the performance of USA team? Well, under hot weather, you do not compare USA against German team because yes, you're gonna win. Not surprisingly, but you compare USA against the best team under hot weather, which is Brazil. When you play under cold weather though, you don't compare USA against Brazil again, because that's meaningless. You know you're gonna win. So you play USA against Germany. And you look at the score difference. And then the overall performance of USA team is max, the worst case, right? That's kind of the way you understand it. Do you follow me? All right. And what's the difference between this and that is that in this case you are comparing against one offline optimal algorithm. But here you are comparing against multiple different online algorithms. That's only optimal on that particular input sequence. Okay, so that's so much I want to say about competitive ratio analysis, online algorithm and instance optimality. Okay. So the theorem for LRU, you can read this yourself, and I will skip the proof. Now let me move on to going back to the DSpace manager. So now we're done with buffer manager. Right? Now let's go back to the DSpace manager. So we understand, per our earlier discussion, we have a fairly good understanding of memory hierarchy. The RAM model, disk, read and write data from disk, and sequential I/O versus random I/O. We have a fairly good understanding of those. However, we still don't understand how database management system manage records and files of records on disk. Okay? So in particular, a file is a collection of pages, each containing a collection of records. And it must support the following operation: insert, delete, modify records, and retrieve a particular record or retrieve a particular range of records in order to support the SQL queries we have defined earlier. Right? So let's look at how the DBMS actually going to support those operations. And in particular, we're going to study this. The basic structure in any DBMS is called a heap file, which is what you're going to implement in Lab 1, by the way. A heap file, so this is where the naming of this is a little bit confusing, because in main memory data structure, a heap, in main memory data structure class, a heap refers to a sorted data structure. Oftentimes heap is implemented as a binary tree. However, in our context, in DBMS, when we see a heap file is not sorted, it's actually not sorted. So it's exactly the composite. So the heap file maintains a collection of pages, and it must keep track of number of pages in the file, keep track of free space on each page, and keep track of records on page. And there are many alternatives as far as how to construct a heap file data structure, and we will consider two alternatives. Here is the first alternative. You basically maintain two linked lists of pages, and there is a header page right here. And header page contains some metadata information, such as the name of the file, which table this file store data for, and so on and so forth. Okay, that's what goes into the header page. And you have two linked lists of data pages. And each data page is of size of your disk page, right? Say 4 kilobytes. The first linked list contains data pages that are almost full, meaning no more space for any new records that can go into those data pages. So you link them together. And then in the other linked list of data pages, you store data pages that do have some free space left that new record can go into. That's kind of like the structure of this this organization. Okay, this heap file structure. Okay. Another approach is, in light of the limitation of this, what is the limitation of this approach? Well, the limitation of this approach, when you maintain two linked lists, is it is expensive to do random access to any single page, because in order to find any page, you have to go through this linked list, right? Which is kind of expensive. So what you do is, to counter that limitation, what you do is you maintain a collection of header entries rather than a single header page for the entire file. You maintain a collection of header entries for all your pages. In particular, you have one header entry for each page in your file. And each header entry maintains some metadata values for that particular page, such as page ID, number of records on that page, free space in terms of bytes on that page, and so on and so forth. Offset location of that page on disk. Do you follow me? So that's essentially the values that will go into that small rectangle box over there. That's what I call a header entry. And this structure allows you to do random access to data pages now, right? Because you can linear scan these header entries to find the page you want, and then just jump to the page. You may argue, wait a minute, you still need to do linear scan over these header entries, right? And if you have n pages, you have n header entries. Isn't the same that you still have to pay other n cost? Well, in internal memory, in RAM model, yes. In RAM model, yes. You need to look at n values. You need to look at n objects. Where in the first case is n data pages, in the second case is n header entries. but nevertheless it's n objects. However, we are operating over disk. Scanning through n pages is totally different from scanning through n header entries. Why? Because each header entry is much, much smaller in size in terms of number of bytes it occupies compared to a data page. That means that you can group multiple header entries in a single page. And remember, when you access data on disk, the smallest unit is what? Is page. So instead of doing n operations over disk, maybe every m of them incur just one I/O, where m is a value that depends on your page size and your header entry size. You use your disk page size divided by the header entry size, that gives you the value of m, which is the number of header entries going to a page. So every m of them, you pay one I/O cost. So linear scan n header entries only give you this much cost versus linear scan n pages. So there is obviously a huge difference because m typically is a big value. You follow me? Okay, so that's kind of this structure. And there are no free lunch, obviously. So what's the downside of this second approach? Well, if you look at the storage overhead, in terms of total number of pages you need to allocate for storing this file, the second approach will occupy more pages than the first approach. Because in the first approach, by the way, the data pages, both approaches roughly require the same number of data pages. Because that's given, that's fixed once you are given a number of records you need to store and page size. That's kind of fixed. The difference is how many pages you need to store those metadata values. In the first approach, you only need one page because you only need to store metadata value for the entire file. Whereas in the second approach, you may need multiple pages. How many of them? N divided by n of them. Because you have metadata value for each page rather than metadata value for the entire file. So you will incur some overhead in terms of that. Okay? So that's the trade-off of the two. I will skip the discussion on index. I will skip this, okay? I will skip the discussion on index. Now, because I will come back with more details later on, so I will just simply skip that. Now we understand how we organize a collection of pages into a file, right? We'll try to build on this, right? We understand how we manage a collection of pages into a file. What we now need to understand is what goes into each page, and in particular, what goes into each record. We all know that each page basically contains a set of records. That's for sure. Okay? But before we understand how those records are organized on that page, we need to understand what's going into each record. And in this case, I'm going to talk about the classic row-oriented storage model. Of course, the new development in database community, there is a parallel approach, an orthogonal approach to this, which is column-oriented storage. Let me explain row-oriented storage first, then I will briefly talk about column-oriented storage. At the end, towards the end of this course, when we have time, if we cover enough of the materials in time, I will, of course, cover column-oriented storage in detail as well. So for now, let's concentrate on row-oriented storage. Okay. With that being said, what's the structure of a record? Well, a record basically needs to contain values for what is defined in the schema of that record. You have to follow the structure of the schema. We're talking about structured data. So now, surprisingly, that's kind of like the structure of the record. The value for the first field, the value for the second field, the value for the third field, and the value for the fourth field. Imagine we are talking about a schema with 4 attributes. But one challenge, though, is how do you know where is the end and start of a value? Because somehow you need to, when you do projection, think about doing projection. If you project out, let's do this. to support this operation, you need to figure out where the value of name locates at from this record. Actually, for each record from the student table, right? Even if I tell you it's the third record, let's say I tell you name is the third attribute from the student schema, you still don't know where that third attribute value starts for each record. Now there are two cases now to discuss. Now is the time to bring back the discussion I had with you earlier when we talked about string attribute in database systems. And we said there are two types of string attributes in a database system, which is, let's say, char20 versus, right? I had that discussion with you. I used that name length example to illustrate the difference between the two, right? So char20 is a fixed length character array of 20 bytes. Regardless of the actual value of your name, you will occupy 20 bytes. Varchar, on the other hand, in the worst case, occupy 20 bytes. If your name value is less than 20 bytes, it will occupy just whatever the length is, that number of bytes. For example, 6 bytes or 8 bytes, depending on the length of your name. In our earlier discussion, we said things like varchar is always a better choice than char because it saves you space. However, there's no free lunch. This is where the varchar comes back and haunt you. Because if you use varchar, you end up with variable length record. In particular, for different records with different name values, the length of the name attribute is different from record to record. In other words, the boundary, suppose name is the third attribute. The boundary between the position of this line will move from record to record. You follow me? And in order to do the parsing, in order to do this projection, so you do need to remember this boundary line and this boundary line. Right? For fixed length record, this is easy, right? Do you need to store this information on each record? You do not. For fixed length record, you can figure out the position of these lines simply from the schema of the relation. Right? Because if I tell you the first one is int, I know this is what? Let's say int, let's assume we're in a system where int is 4 bytes. So we know this is 4 bytes. And I tell you the second attribute is a float, so that's 8 bytes. So 12 bytes. If I use char20, I know this is 20 bytes. So where is this line? That's 20, that's 32, that's the 32 bytes. That's where this line is. And this is where the 12 bytes locates at. So I know how to do the parsing for every single record. I just look at the bytes between the 12s and 32s. That's the value of my name for any record in my schema. I don't need to store this information with each record. I can do that simply by looking at my schema definition. But for variable length record, this is no longer the case because this line moves. So somehow you need to remember where the line is for each individual record. That obviously causes overhead. And there are two ways of doing that. The first approach is to remember a special delimiter between values of different fields. Suppose I use $sign. Imagine $sign, this dollar character is never used in my entire database. It's a special character I reserve for my system. I can always do that. I can define a character I do not expose to the outside world. It's only viewable to my kernel, and nobody can use this character, 1 byte. Do you follow me? It's a single byte, okay? Single byte. So suppose $sign is a byte. Of course, in real system you cannot use $sign because databases do need to store dollar values. But just for the argument's sake. Then you insert this delimiter between any two values for a given record. And the position of this dollar sign may move from record to record, that's okay. And with this delimiter, you can do parsing already. You can do projection with no problem, right? All you need to know, you still need to know the order of your attributes, meaning whether name is the first attribute or the third attribute. But that can be figured out from your schema definition. You follow me? You don't need to store that information per record. So you simply pass the record using this delimiter sign, you get the value out for each attribute. A downside of this approach is that you do not support random access at the record level. If you want to jump to the third attribute, you cannot easily do so because you don't know where that third dollar sign located at. You have to do a sequential scan from the beginning to locate the third dollar sign. You may argue a record is small. This is not a big problem, but increasingly in big data application, a record becomes larger and larger with more and more attributes. It's not uncommon to have a record with hundreds of attributes. So every time to do projection, you need to do a linear scan from the beginning. That can be expensive, even at the record level. So that motivates the second approach, which is similar to this, but we apply the similar idea to the record level. Essentially, we maintain what we call a directory right here that tells you the offset value for each field on this record. And these values may change from record to record. That allows you to do random access. You may argue, why do you always use this versus this? Well, this introduces more overhead. Why? The delimiter approach, if you have n fields, the overhead is simply n bytes, or n minus 1 bytes. Actually, you need n bytes because you need this one to separate this record from the next record. Suppose records are next to each other. You do need the last dollar sign. Okay? So if you have n fields, the overhead is simply n bytes because you need n dollar sign. Each is 1 byte. Whereas in this case, what's the overhead? You need n offset values. And this is no longer n bytes because the offset value may require more than 1 byte to represent. Right? You follow me? 1 byte can only index up to the power 8 is 256. Right? So 1 byte can only give you an offset value up to 256. If your record length is more than that, your offset value must be more than 1 byte. So it introduces more overhead. Okay? So that's the record level. Now we understand what goes into each record. By the way, this is essentially what you have to implement in Lab 1. But actually, good news for you guys, Lab 1 use fixed length record. Okay, fixed length record instead of variable length record. So it's much easier to implement. Now, once we understand what goes in the record level, now let's look at what goes at the page level. So a page contains a collection of records, right? But how you organize these pages, this record into a page, again, it differs from whether you're talking about fixed length record versus variable length records. For fixed length record, again, it's easy. There are two approaches essentially. One approach is on the left-hand side, which is what I call a packed array. Imagine you divide your page space into two regions. The white region is what we call the record space. So they contain your records. And then the black region is what we call the free space. The space that can be used to store additional records onto this page. And each of these rectangular blocks represent a single record. Keep in mind, we are dealing with fixed length record now. So the size of each box, smaller box, is fixed. So I can actually pre-calculate how many, I call each small rectangular box a slot. You can actually pre-calculate how many slots you can have on a given page once you know the page size and record size. You use page size divided by record size, take the ceiling of that, take the floor of that. That gives you this value n here. Do you follow me? And the packed structure is efficient for insertion because you always insert at the next slot or at the beginning of the free space. But expensive for deletion. Why? Because if you delete any slot, any record from a given slot, you need to do what? You need to do a packing operation. Keep in mind, when you do that packing operation, don't move record one by one. You do a man move for that entire region ahead by the size of one slot. You use man move to do that. This is in C context, right? Essentially, you move an entire memory region to another location instead of moving record one by one, which is much more expensive because you end up calling multiple, you end up doing multiple function calls versus just doing one function call. Function call costs you time, right? You know that, right? Every function call, you have to allocate stack and all that stuff, so it costs you time. Imagine if you have 100 records here, after the deleted record, you are making 100 function calls versus making one function call. So there's a huge difference. Okay? Versus the other approach, which is in light of the deletion might be expensive. The other argument is okay, let's do not pack the record space. Meaning I may have this free space in between records. Okay, because of deletion, right? And what's the downside of this approach? The downside of this approach is somehow you need to figure out a given slot is storing a record or just storing some random bytes. How do you distinguish whether it's a white slot or black slot? You have to figure that out, right? In this case, you don't, because all you need to remember is the boundary line, where the boundary line is. That's a single value. Oh, by the way, this n denotes, I said something wrong earlier. I said n is the total number of slots in a given page. N is total number of record slots on a given page in this notation, right? So n, this value n tells you the boundary between white region and black region. So whatever value less than n in terms of slot index, that indicates it must be a record. Whatever value greater than n, that indicates it must be a free space slot. Okay? So a single value does the magic for you. Whereas in the right-hand side, you can no longer do that because they are mixed together. Right? So you need what we call a bit map. A bit map is nothing else but an array of bits. Array of bits. Not a byte map. Not an array of bytes. Array of bit. Not a single byte. There's a huge difference because that determines the space overhead. The space overhead for a bit map of size n is n over 8 rather than n in terms of bytes. Okay? That's almost an order of magnitude difference. An order of magnitude is 10, right? Divided by 8 is almost the same as divided by 10. So there's a huge difference here. So what you do is, suppose your page can contain up to m slots. M is what I said earlier, which is page size divided by record size. Take the floor of that. Total number of slots you can actually store. And to be precise, the value of m needs to be, it's a function. It's actually a formula, the equation you need to solve, which is use p minus this divided by the record size. Take the floor of that. And you solve this, you get the value of m. Because you do need m over 8 bytes to store the bitmap. That cannot be used to store the record. Right? That's the reason why. To be precise, you also need to minus 1 because you need to store the value of m itself, which is a byte. Why 1 byte is enough? Because typically you don't, 1 byte is enough to represent 256 slots. And that's a lot of records on a given page already. So typically 1 byte is enough for the value of m. n is less than 256. So that's the value of n. This is 1 byte followed by n bits, either 0 or 1. And then that tells you whether a given slot is white or black. Okay, so that's this structure. But both are relatively easy, right? They deal with fixed length records, so that's easy. What about variable length records? You can no longer use simple structure like this anymore, right? Because the white slot and black slot, they are no longer the same size anymore. Using this bit map approach will no longer work. So how do you do this? Well, the data structure is like this. It is actually a modified version of the bit map approach. So in addition to that bit map, right, to modify this, what do you need? Well, you need to remember, for variable length records, what do you need to remember? You need to remember the offset position of a record on a page and the length of that record. As long as you have these two pieces of information, you can decode this whole thing. Imagine this is kind of like an equation, right? In order to decrypt the page, what do you need to know? You need to know the offset and the length, the values for the offset and length for each single record on the page. Once you know that, you can decode the whole page. Do you follow me? And it's kind of like when I try to encode you guys, in this classroom setting, what do I need to know? For each one of you, I need to know your row number and your column number. That's it. Once I know your row number, column number, I can restore the whole classroom sitting map, no problem. Okay, that's kind of the idea. So it's actually quite straightforward. The idea is, again, you divide the black region, or this light blue region. Okay, the white region is record space, the other part is free space. And by the way, you do pack the record space, meaning the entire white region is packed with records. There are no free space left in between any two records. This actually introduces some complication that I will introduce next. Okay? And what do you do? What you do is as follows. First of all, you need a value to remember the boundary line between free space and record space. And this is represented as a pointer, but in reality it's not a pointer, it's simply an offset value. The value of this is in the range of 0 to your page size, because that's what the maximum possible offset value is. If you have 4 kilobytes for a page, the possible value for this is from 0 to 4096 bytes, roughly, right? Because you need to, this value cannot go beyond this array here, but roughly 4096 bytes. And this offset value, you can calculate this with respect to the beginning of the page or with respect to the end of the page. Doesn't really matter, right? Doesn't really matter, as long as you are consistent in the way you calculate this offset value. You follow me? Okay? And then followed by a value called n, which denotes the size of this array, which is what we call a slot array, slot directory. This value n denotes the number of elements currently in this array. And now what's an element in this array? Each element in this array is a pair of offset and length. That's it. So we have n such pairs, which means this array has n elements. Okay? Now let's look at the first element. The first element says 24, that's the length of that record. And there's a pointer. This pointer is nothing else but that offset value. Imagine all these pointers are simply offset values, calculated with respect to either the beginning of the page or end of the page. Let's say we calculate this, use the beginning of the page. So roughly this is the halfway through the page, right? So this might be 2000. This value might be 2000. That means it's 2000 bytes to the beginning of the page. You follow me? So that's two. If this is 2000, what's this value here? 2024, because the length of the record is 24. Now let's move on to the next element in the array, which is at 16, and this. This is roughly maybe 1500, right? So this is 1500, and that's 1516, 1516. So on and so forth. Now let's move on to, we go all the way to the last element here. This might be, I don't know, let's say the 8 bytes. As this length is very small, so this offset is 8, this is 20, so this is 8, this is 28. That's it. This is a structure, okay? If you have no insertion and deletion, this is actually very easy to understand. Now let me introduce another concept called record ID. Record ID is a unique identifier for a given record. And it consists essentially of two parts. One is page ID, which page this record locates at, and slot index, which slot entry corresponds to that record on that page. So for example, suppose this is the page I, the record ID of this record is simply I and N. Do you follow me? So one thing that's somewhat confusing to some of you is record ID. The first part is always the same for record on the same page. It's always page ID. The second part, the value of the second part is not the same as their sequence in the record space. Even though this is the first record in record space, it may be taking the last slot entry. That's possible. It's not in any particular order. Okay? That's because you have to support dynamic insertion and deletion. Okay. Now let me talk about, show you how we do dynamic insertion and deletion. Okay. Suppose this is my initial setup. Do you follow me? So there are 4 records on this page. This is the I1. I2, I3, and I4. Start at 0, then it's 10, so this is the 10th byte. That's why, if you look at I2, the offset 10, then it's 8. So I3 must be 18 and 12. So this must be 30 plus 5, so that's why this space is 35. The position of that free space and record space is at the 35th byte. And the value is 4. There are 4 slot entries. Okay? Now, for insertion and deletion, what do you do? For deletion, let's say I want to delete I2. I want to delete this record I2. I want to delete I2. So you may wonder where that delete come from? Well, delete from student where student ID equal to 1, 2, 3, 4. And so happen that student record is represented by student ID equal to 1, 2, 3, 4 is translated to this record ID I2. That's what this deletion, where this deletion come from, okay? So you want to delete that record. What do you do? Well, obviously you need to remove that record, the entire record from the page. But one thing to keep in mind is record space must be packed. You cannot leave a hole there. Why you cannot leave a hole there? Because if you do leave a hole, and since you are dealing with variable length record, that hole may never be utilized. What if your future insertion of record all have lengths larger than the space of that hole you have left behind? You can never reuse that hole. You follow me? You may argue, that may not be the case. I will always have some record whose length is less than a record that's already been deleted. Fine, you can go into that hole, right? But you always going to leave some hole in between, right? Unless you have another record perfectly match the length value of a previously deleted record. That may not happen in a variable length setup. That's why you cannot leave any hole in record space. You do need to do the packing operation. Do you follow me? Yes? So we have to do the packing operation. That's easy. We can move those guys forward by how many bytes? By the length of the deleted record, which is, in this case, 8 bytes. But the tricky part is how do we figure out from where to where we need to move forward by 8 bytes. Well, this value is easy to figure out. The beginning address for the region to be moved is simply the offset value plus length for the deleted record. And what's the end value of the region you need to move? Well, that's simply the value here. So it's very easy to figure out these two values. So you move them, map move, using that region, the beginning address and address. You move forward by how much? Well, by the length value of the deleted record. That's easy as well. But the question is, are you done yet when you do this? Well, not necessarily, right? You're not done yet. Once you have done this move operation, do this packing operation, one value you need to update, which is this value here, which is the boundary between free space and record space. That should be updated by the length of the deleted record, either minus or plus. Why? Depending on how you calculate the offset value, with regard to the beginning of the page or to the end of the page. If you calculate this with regard to the beginning of the page, you need to do minus. Otherwise, you need to do plus. The length of the deleted record. And you are not done yet. Why? Because the offset value for those records who have been moved are affected. In particular, the offset value for these two records need to be updated by the length of the deleted record as well, either minus or plus. In our case, it's minus because I calculated the offset with regard to the beginning of the page. The only question left is how do you figure out where those offset values locate at? In other words, which slot entry corresponds to these two records? Keep in mind that you can go from slot array to the record, but you cannot go from record to the slot array unless you are willing to spend some more overhead storing a slot array index with each record. But that's introducing additional additional overhead. You follow me? So how do we figure out which slot entry corresponds to those records that are being affected? Can someone tell me how we do that? Yes?
Well, if you know it's packed, if anything has an offset greater than the one you moved. Right?
Fantastic. You know those records that will be moved must have offset values greater than the offset value of the record that has been deleted. Suppose you calculate offset with regard to the beginning of the page. Otherwise, they must have offset value smaller than the record being deleted. So that's exactly what you do. You move them, and after you done move, you update this value and you scan through the slot entries. For each slot entry whose offset value is bigger than the offset value of the record that was just deleted, you update their value by minus the length of the deleted record. So 30, let me move my mouse over here, become 22. And then 18 become 10. But for this one, you do nothing because the offset value is smaller than the offset value of the deleted record. What about the deleted record itself? Meaning the offset value equal to the record to be deleted. Well, there are two choices. One is you deallocate this slot array and you pack the slot array as well. You deallocate this slot array element, you pack this slot array. But the thing is, if you do this, for future insertions, you need to allocate slot entries. So the idea here is, keep in mind, even though records are variable lengths, slot entries are not. They are fixed lengths. Slot entries are fixed lengths. Right? Because each has offset value and length. The values are different, but the number of bytes needed to represent those values are fixed. An integer or whatever, right? A few bytes. So we can actually recycle them without packing operation because they are fixed lengths. So that's exactly what we decided to do. We denote the slot entry that was just deleted corresponding to a just deleted record by -1, -1. Then for future insertion, next insertion, I can reuse that slot array entry. Okay? And insertion is actually easy. You always insert at this address, and by expanding this value by the length of the newly inserted record. Okay? So that's the insertion and deletion for variable length record. Good news is lag 1 doesn't require you to do variable length record. Lag 1 you do fixed length record. But you do need to understand how variable length record works. Okay? Now let's talk about system catalog, then I will spend some time on lag 1. We keep saying, okay, when we talk about fixed length record, like this, I said for fixed length record, you don't need to store the delimiter or this offset value for each record because you can figure out this boundary information by simply looking at the schema of the table, right? But one question remains is where I can find the schema definition. Where can I know all these values? Where can I find all those values? Well, those values are stored in what we call the system catalogs. For each relation, we typically store the name, the file location, the file structure, the attribute name and type for each attribute, index name for each index, and so on and so forth. For each view, we define the name and the view definition for each. I will skip index now because we haven't talked about index, right? And here is an example of a system catalog. In most database systems, system catalogs, what's interesting is system catalogs themselves are stored as tables. They are simply stored as tables. They're just special tables. They're not your database tables, they're system tables. But the structure of them is the same as another database table. They also have definition, the schema, and instance. Okay? So here is an example of this. And in particular, I'm going to use our so this is not the latest version. Let me download the latest version of this. Okay, let me pull out the latest version of the slides, then I will go over from here. So this is system catalog, and I'm going to show you system catalog from PostgreSQL database we have. Okay, and then from there I will go to lag 1 directly. So for example, I'm going to do the mode. Okay, so now I'm connected to the DVD rental database, right? So if you do this, it shows you the schema, this information, right? So this schema, as I explained before, is not the relational schema we talked about, right? This is kind of like a namespace in your C++ program or Java. Java doesn't have namespace, but you know, if you know C++, you know what namespace represents, right? Or in Java sense, it's kind of like a package kind of thing, right? So user tables are typically in the namespace of public schema. That's what we call the public schema. Those are the tables, the actual user tables for your database. You follow me? And those additional, you may wonder what are those additional ones? PJ catalog. That's essentially the catalog tables, and they are in the namespace of catalog. That's why you don't see them. Typically, you don't see them. Typically, if you do, for example, if you just do DP, by default, they only show the tables from the public namespace. It's the same as this, essentially. Now, I want to focus on the the catalog tables. Here you can see a lot of different things. For example, in particular, we're going to look at PJ class, PJ attribute definition. That's where the attributes are defined. PJ class, that's where the tables are defined, and so on and so forth. In particular, let's say we look at the schema information for PJ class. That tells you it's from the schema catalog. It has a name and type and owner and so on and so forth. If I look at the attribute name, what is it called? Attribute PJ ATTRBF. Okay. Well, A or PJ ATTRBF. Okay, so that's the definition of this. If I look at the definition of it, now if I select from this, because remember these are just tables. These are just tables. Like I said, catalog information are stored just as tables. So I can select from them, and that gives you things like this. Basically, that's what each attribute is defined. This looks messy, so let me run some queries for you. So if I copy this, I want to run this query. Okay? And what this tells me is all the relation names in my database. OID is a kernel identifier for each object in the database. That's a special kernel identifier for each object. So as you can see, these are all the table names. Okay? You follow me? Now, if I run the following queries, where PJ attribute contains metadata about attributes of all relations, right? So if I want to find, let me run this query first, then let me explain what this query does. Okay, I cannot copy from. Okay, this should fix it. Okay? Can you tell what this does? It tells me the OID. The attribute name, attribute type ID, and attribute length. The OID, by the way, this is the OID for the payment table. I can prove that for you by running the previous query again, where relation name like just equals. Right? I know I'm looking for this guy. So the OID of this table is this. So that's what this OID is. I'm doing a join between PJ class and PJ attribute. And what this query tells me is all the attributes from that table, the type ID, and the length of each attribute. The type ID defines the type of the attribute, which is available in yet another catalog table called attribute type. You follow me? So if I want to find out the type of attribute, what do I do? I can run the following queries. So let me remove this. So if I run this query, so I get the type information. And this is over the customer table. Do you follow me? And you can run these, the other ones you can run by yourself, but the bottom line is catalog are tables themselves. And they store information about your schema definition, the attribute name, and so on and so forth, and type information. Do you follow me? And that's, again, what you need to do for your lab 1. That's actually the first step in lab 1. You need to register your catalog and register your tuple information, table definition, and so on and so forth into your catalog. That being said, let me run my simple DB. I'm debating whether I should boot to Linux or not. And do that. But I'm worried that once I'm there, I cannot manage the internet. Some problem with this. I need to use my Ubuntu distribution. That one you can do it in either Linux or Windows or Mac OS. But I strongly recommend you do it in a Unix-based system. But Windows works too. Okay, so, all right, so this is lab 1. By the way, each of you will be able to get an account from Georgia, the database server we use, not the database account, Unix user account. So each of you has your own user ID and password, because we have set up everything you need to have on that Georgia server. So you can do all your development there if you prefer. But if you want to do it locally, suppose you want to use IDE with GUI interface, then you cannot use Georgia for that purpose, right? You can still do it locally. But we have set up everything you need to have, including Ant and Java, all the environment properly set up on that server. So you can always do it over there. You can get that user ID and password by sending an email to our TAs with your team information, who is your teammate and so on and so forth. If you are by yourself, simply let the TA know, I'm by myself. If you're in a team, send both of your information to the TA. We need your name, UID, and email. Now, so I have, this is a complete distribution of single BB, which I demonstrated to you before. By the end of semester, you will build something like this, right? So when you run this, and I load the database with this MDB database, and you can run queries like which shows you the query plan and the output. Okay? That's a simple query. And the definition of this is in this schema right here. And the data is, I'm using this particular data over there. For example, I can show you the movie table. Okay? So that's what I did just now. By the end of semester, you are supposed to build a system like this. Of course, we cannot do this over one lab, so we break up this into multiple lab sessions. The first lab session asks you to do buffer, heap file, catalog, schema definition, and a simple scan operator. Scan and scan all records. That's what you need to do for lab 1. Let me show you how that works. And this whole thing is done using Java plus Ant. Ant is something just like make. Right? It's a configuration tool. Right? So the way you do it, this will compile the whole project. And you want to run a particular test, you run Ant test. And we use, in particular, we use JUnit to run all the tests. Okay, so this is running all the tests. I'm going to cancel it. Now coming back to your distribution lab 1, okay, this is lab 1, right? What you do is you do AND distribution that will build your distribution, and if you try to run tests, what happens? Obviously things will fail because you haven't filled in any code. You haven't run any code yet. You know what I mean? If you want to run a particular test, because the test has many different tests, if you want to run just this particular test, what you can do is AND run test, catalog the test name. You give a name to the test, which is called the catalog test. And that will simply run this one test. You don't have to take note. All these are available in the lab 1 distribution from the course website. At the end of the day, what you do is run each JUnit test one by one to debug your code slowly, right, incrementally. At the end of the day, your code needs to pass what we call the system test. The system test basically is doing this scan operation. Register the table, register the catalog schema, insert records, and do the scan. And read data into buffer and scan. And that's how you do it. And I have to overrun the process a little bit. I will show you how to do this in Eclipse as well. If you download the latest version of Eclipse, you can run the whole thing in Eclipse as well. You import the projects into Eclipse, which I have done. I gave instruction how to do this on the website. The build.xml, which is used by the JUnit AND. And then you can do run as, right click and run as and build. Here, allow you to select what to run. You can select test and system test. And this is the same thing as you were running at terminal. Or, alternatively, you can go to the test folder, SimpleDB test, click on any one of the tests. Each one of them is a JUnit test. Eclipse will be smart enough to figure out that it's a JUnit test. You can right click and run that as JUnit test to test each individual test. You follow me? And system test is under SimpleDB system test. And this is that system test. Again, you right click, you can run this as a JUnit test. The goal of lab 1 is to pass this test. Okay, that being said, I have distributed everything you need to know for your lab 1. You should get started. Okay, thank you.